Good morning. One second only.
Professor Massimo, your microphone is switched off.
How about now?
Okay.
Okay.
Now it's okay. So just 1 second that I load the notebook. Okay, so very good. Yes, so I'm ready. Yes, sorry about that. Okay, so today is November 24. And we start our lecture by proving that Morrey spaces, weighted Morrey spaces, generalized Morrey spaces are complete, okay? So theorem, we start with this theorem here. And then as usual, let V in 1 plus infinity. And W, as usual, weight from 0 plus infinity to 0 plus infinity. And let me add, let W be non-trivial. By non-trivial, I mean not identically 0. It is identically 0, does not. Okay. So here we mean W is not identically equal to 0. This means that exists are 0 such that W over 0 is not 0 for at least 1 point. Otherwise, everything becomes trivial, okay? Then the Morrey space, the generalized Morrey space, W p omega is complete. And accordingly, Wm p omega is a Banach space. So you remember what we have to do? So we must show that if you have a Cauchy sequence, if Uj, J and N is a Cauchy sequence, in the Morrey, generalized Morrey, then there exists U, let's say, in the generalized Morrey, such that limit Juj equal to U in the Morrey space. So according to the Morrey norm, I mean this. Okay, so we want to try this. So now you remember that we proved already that, so remember that the Morrey space is continuously embedded into the LP local, and that accordingly we have that the restriction map. Actually, more than this, we remember that actually I could write more than this. This is true. This is certainly true, but I need more. I remember that if, sorry, let me say something stronger than this. This was perfectly okay, but I need something stronger. That if R is greater than 0, then the restriction map. So this was not an accord. Then the restriction map that goes from the Morrey to LP of the XR intersection omega that takes a function f to the restriction of f on the XR intersection omega is linear and continuous. We have already proved this. You also remember that the linear and continuous maps are also uniformly continuous and maps Cauchy sequences to Cauchy sequences. We also remember that linear and continuous maps between norm spaces map Cauchy sequences to Cauchy sequences. And even if you don't remember it, you can prove it in 1 second just by writing the boundedness condition for the corresponding operator with the norms. You estimate the norm in target space with a constant times the norm in the domain space. Hence, the sequence uj, so we called uj, yes, uj, restricted to is a Cauchy sequence in the complete space, in the Banach space. The target here that is was LP BXR intersection omega, okay? Okay, so what's the consequence? So you have a Cauchy sequence of these restrictions, then the sequence of the restrictions. Actually, we could also use a small r here, maybe beta small r instead of big R, because it's uniform with the rest of the notation that we used in the last days. So BXR, it's okay, BXR, sorry. Correct this misprint. You use small r uniformly instead of big R, capital R. Okay, so we have a sequence now in this space here. Hence, there exists an element which we call it VXR, because we have fixed the point X, if R and X is in omega, of course. VXR in the space, in the complete space Bxr, such that uj restricted to Bxr intersection omega converges to Bxr in LP. This is a Bxr intersection omega. Okay. Okay, but we also know that when you have a sequence that converges in LP local or here in this LP here, you can extract a subsequence that converges almost everywhere. Okay, so since now we use the information M W P omega is in LP loc, as I wrote before, omega. We have that lim uj equal to I'm sorry, we have let me write better. There exists U in LP loc such that uj lim equal to U in LP loc. Let me remind to you what this means. Maybe everybody knows it, but just to remember what it means. That uj restricted to k converges to U restricted to k in LPK. This is just a real analysis, brush up for all k containing omega k compact. Okay. Saying that you have a convergence sequence in this LP loc means this. This is just a standard real analysis. And we also know that by real analysis, we know that if you have such a convergence, there exists a subsequence, jk k in n, such that the ujk that converges to U in LP loc, of course, because it's a subsequence, converges to U not only in LP loc, but almost everywhere in omega. That I write normally O A E in omega. Okay? And then of course, but you also have that the uj on the Bxr intersection omega was converging in LP to Bxr, in particular here. The ujk converges to Vxr. I'm sorry, this is restricted to Bxr intersection omega. Okay, why? Because if the convergence happens almost everywhere in the entire omega, then of course, a fortiori, it happens and takes place in this subset. You see, this is a subset of omega. Okay, but then the ujk converge almost everywhere here, almost everywhere in the subset of Bxr. intersection omega. But in the very same subset, you have convergence in LP. Hence, sorry, not you. Converges everywhere in omega, almost everywhere in omega, and therefore in this subset. But then you look at this, and then you look at this. Hence, you have that U restricted to BXR intersection omega, it's equal to VXR almost everywhere in BXR. Okay. As a consequence, then they determine, of course, the same equivalence class in LP. Okay, because they are all equal almost everywhere. And then here, let me see that I have to generate an extra page that I forgot. Okay, so as a consequence, since U is equal to U restricted, it's equal to V, which is just about, and accordingly, now I rewrite what I wrote before for UJK. For UJ, can you see it in the green, the upper green one? I have that UJ restricted to BXR intersection omega converges in LP BXR intersection omega to where? We said above in the green here to VXR, but we just said that VXR coincides with the restriction of U, so I just rewrite U restricted to VXR intersection omega. Clear, right? That's obvious because we showed that they're equal almost everywhere. And next, what is our next step? Next step, we turn to show that this element of LP local that enjoys this nice property, U actually becomes an element of, is an element of WP omega. This is our next goal, what we are going to do now. And to do this, we have to control the Morrey norm. So we start, write WR, then we put as usual U in where? In BXR LP. And we have to estimate, right? Estimate it independently of X and of R. What information do we have? We have this information that I just wrote here. We are going to use this one. In order to use it, we use triangular inequality. So we write WR U minus UJ LP BXR intersection omega for an arbitrary X and arbitrary R plus WR UJ BXR intersection omega as usual. Okay. Now, what do we know? We know that if you take the supremum on R and on X, the second addendum on the right-hand side is estimated by the Morrey norm. So WR, let me rewrite here. And U minus, here I just copy, okay? Sorry, BXR intersection omega plus UJ Morrey norm WP omega. remember that I wrote this independently of the point X and the point R. So you just fix the way you want, and this is certainly true. What do we do in the next step? Now we remember that Cauchy sequences are always bounded. In normed spaces. Immediate consequence of the triangular inequality. This means that you have a uj for some j. Well, the sequence of uj is Cauchy, uj is Cauchy in Morrey, then automatically, just because Morrey is a non-space, the sequence here is bounded, so this is less or equal than just write WR, U minus UJ, and B, BXR, section omega, plus the supremum L in N, U minus, sorry, what was it? UL, Morrey, W P omega. Of course, this is just one of the norms of the elements of the sequence. And here we are taking the supremum on all possible norms of the elements of the sequence. And we know that this supremum is not an infinity, it's a finite number. Next, what do we do? So we proved that so far, let me change color, because I want to emphasize that we proved that blue less or equal than this. Okay, and this happens for all j in n, for all x in omega r greater than 0, the blue one. Okay, so what are we going to do next? Next, we are going to exploit the information we have that the uj restricted to this ball intersection omega converges to u restricted to ball intersection omega. Fine. Then we are going to exploit now that maybe another color, maybe orange, that the uj is converging to u in LP BXR intersection omega. Right? We said this one moment ago. Fine, then you can take the limit as j tends to infinity, right? Next, we take the limit in the blue inequality as j tends to infinity. And we can do it because we have the orange information and obtain what? Copy WR U LP XR intersection omega less or equal. I write the W, but because of the orange information, I write here 0 because when you take the limit as j tends to infinity, uj goes to u, right? Plus supremum L UL Morrey norm. And hence, this is going to be true for all x in omega r greater than 0. R greater than 0. Hence, if the supremum in the left-hand side is bounded independently of the point x and of the radius r, we have that u belongs to the Morrey, and the norm of u in the Morrey is less or equal than the supremum L UL Morrey omega, which is less than plus infinity, of course. So now we know that U is Morrey. Next, what we have to show, just the uj converges to U in Morrey. Next, we show that uj converges to U in Morrey, in the Morrey norm. When you say in Morrey, it means in the Morrey norm. And we can write this because uj is actually an element of Morrey. U is actually an element of Morrey. We just proved it. It just asks now where we have convergence. And now we do the job, and we start from the information that we have in the assumptions. We remember that uj is Cauchy. In Morrey, right? This was the assumption. Now let epsilon greater than 0, which is what we are going to use to show that uj tends to U. So the difference in norm will be less or equal than epsilon for sufficiently large j. This is what we want to show. And then we know there exists a j0 such that by definition of Cauchy sequence, uj minus ul Morrey wp omega is less or equal than epsilon for all indexes j and l greater or equal than j0. This is saying that it is Cauchy, and this information that we have. Now I want to rewrite this information, actually rewrite the consequence of this information. In particular, hence, since we have this inequality, you remember the definition of Morrey norm. So WR times uj minus ul LP of bxr intersection omega is less or equal than epsilon for all jl greater or equal than j0, not only for all x comma r in omega times 0 plus infinity. For all possible points x of the set omega, for all possible radii r, which are strictly positive. Then next we remember that the ul, however, we already know that the ul to be intersection omega tends to U restricted to the XR intersection omega in LP. Oh, that's what we wrote before above. Just go back and see it. Then what I do is this tends to U, right, as L tends to infinity. Hence, we take the limit as L tends to infinity. In which space? In the space in LP. I'm sorry. As L to infinity in the above inequality. Inequality. And obtain. Okay, this limit in LP, as L tends to infinity, UL tends to U in this LP here, right? But the norm is continuous. So we have WR uj minus 0. No. Sorry. Minus 0. Minus 0. Right? And this inequality here holds for all x's in omega and for all r's. Then I can take the supremum. Next, we take the sup in variables xr and obtain that the Morrey norm in the Morrey space MWP, which is precisely by definition the supremum as xr tend to belong to omega times 0 plus infinity of the WR uj minus u is less or equal than epsilon, right? For all possible j greater or equal than j0. But this is really saying, so sorry, that I have to produce another page. And when you write this, that for each epsilon there exists a j0 such that the uj minus u is less or equal than epsilon for j greater than j0, this means the limit right? This is just the definition of limit, or an equivalent condition to the definition of limit. And the proof is complete, right? Hence, is complete. And this is the end of this proof. Now there is a particularly important subspace of the Morrey, which is the vanishing Morrey. And now we show that also the vanishing Morrey is complete. And to do it, we just show that the vanishing Morrey is a closed subspace of the Morrey. In order to show that also MW, 0 P omega, the vanishing Morrey, is complete. We now show that the vanishing Morrey is closed in the Morrey. So this is what we're going to do in one moment, okay? So theorem as above, open. And then W is our usual weight, which can vanish, but not identically. Non-trivial. I don't want it to be identically equal to 0. There's nothing to say otherwise. Then proof, you remember what we have to show. We have to take an arbitrary f, which is in M and in the closure of the the vanishing Morrey, and show that actually this element is in the vanishing Morrey. So let f belong to the space MW without the zero in the Morrey, and let f be in the closure of MW0P in Morrey. Then we know that there exists a sequence Fj, as in all non-spaces this happens, in the vanishing Morrey, such that the Fj converges to F in MWP omega. So remember, F is in the closure of the vanishing Morrey, then there exists a sequence of elements of the vanishing Morrey which converges to F. So what we want to do now is to show that F is in the vanishing Morrey. We need to show that. F that belongs to the Morrey actually belongs to the vanishing Morrey. This is what we must prove now. And maybe you want to remember what it means. Remember what was the definition of vanishing Morrey, that the limit as rho tends to 0 of F rho WP omega was equal to 0. This is what we need to prove, right? And in order to estimate this modulus here, we start as usual, and we estimate to do so. We estimate WR in order to estimate this modulus here, F LP BXR intersection omega. When X is an arbitrary element of omega, and when R is a positive number, which is less or equal than rho, for let me write this way, for X in omega, and I'm sorry, radius between 0 and rho, so that the supremum is really this modulus here. So let me estimate this. So this is less or equal to what is the information we have. We know that Fj converges to F. We want to use such information. The most natural way to do this is use triangular inequality. Fj by the way, intersection omega, I forgot. As always. So no problem about this one. And this is less or equal, then you can take the supremum in R and in X, and this is less than the modulus F J rho W P omega, and we know that for each individual J, this is going to tend to 0 as rho tends to 0, because these Fj's are in the vanishing Morrey. Okay, plus now you take here the supremum on not only here I take R, which is in 0 rho, but I allow it to be R just a positive number. I take the supremum in all possible R's, not all on the R as I did here between 0 and rho, but all possible. And in X, and nothing else because I have, and the X in omega, I'm sorry. And this is going to be less or equal than F minus Fj plus infinity of WP omega, because it is the supremum of the second addendum, as X is a point of omega, and R is between 0 and plus, even plus infinity. But then we have proved that, hence, you see, now you look at maybe here, the left-hand side, and this. So in the orange, I want to take the supremum as X is in omega and R is between 0 and rho. Hence, by taking the supremum, sup as X R in omega times 0 rho, sorry, in the inequality above, I mean the orange one, we have F rho WP omega less or equal than Fj rho WP omega plus F minus Fj, sorry, nothing here. And well, actually I could, why not the norm? It's absolutely equivalent. This is the norm. I could write any of them. W, any of the two, say. Okay. Remember, our goal is to show that the left-hand side goes to 0, a rho tends to 0. But now we are, roughly speaking, done. So now so we now show that we are now ready to show that limit rho tends to 0 of F rho WP omega equal to 0. We are ready to show it. Why? So let an arbitrary positive number, for example, eta, greater than 0, then you see the Fj converges to F by assumption, right? So there exists a J0 such that F minus Fj less or equal than eta over 2 for J greater or equal than J0. But in particular, also for J0, right? Okay. And next, since F of 0 is in vanishing order, then the limit as rho tends to 0 of Fj rho WP omega is 0, right? By definition of vanishing Morrey space. And thus, there exists a rho eta, let's say rho eta, for example, such that the Fj 0, rho WP omega is less than eta over 2 for rho just a minute to generate in the page. Hence, so let's look at the inequality above. We have that F rho WP omega less or equal than. So here, this inequality here, I'm using the green one maybe. I'm looking at the green one. For J0. So we said that if J is greater equal, and therefore also for equal to J0, this norm here on the right-hand side of the green inequality is less or equal than eta over 2. And we said that for rho between 0 and rho eta, fj0, this first term on the right-hand side of the green inequality is also less or equal than eta over 2. So you can write eta over 2 plus eta over 2 equal to eta if rho is in 0 rho eta. Okay? Because this was less or equal, greater or equal than this. Okay? Very, very good. So, but when I say that for each eta, there exists a rho eta such that for rho smaller than rho eta, this modulus is less or equal than eta, this is saying that limit rho tends to 0, f rho w p omega equal to 0. And accordingly, f is in a vanishing Morrey. And this ends the proof. Now let's see some consequences of the fact that the vanishing Morrey is closed. Hence, if you want, so proper as a consequence, we have the following. If you want proposition, but just one moment, I have to plug in the electricity. Nontrivial. Now let me see. This is just really an exercise. You remember a closed sum of a Banach space is a Banach space. So W0 p omega comma 0 here. A Banach subspace of W p omega because it's closed, right? First, and this is, I leave it as an exercise, but if you take the intersection W p omega middle p, this is Banach, and P, this W is Banach, so this is Banach. With the norm that we have already seen, by the way. Maximum by the way, it is always true that if you have two Banach spaces and you take the intersection and you use the maximum of the two norms as a norm, then you still have a Banach space. Or you can prove it in general. For this specific case, it's an exercise of one line. You take a Sikorsky sequence in the intersection and you show that there's a limit. Well, there's a limit in both the spaces. So, okay, so then as a consequence, you remember that MW0, the vanishing, is closed. So MW0P intersection P omega in B space, subspace of WP omega intersection P. Then, did I have anything else to say? Oh, by the way, I leave you also this is an exercise. We got kind of everything. So if you remember equal the infimum of W is strictly greater than 0. In this case here, do you remember that we had the embedding of Morrey into the LP, right? So then Morrey WP omega intersection LP omega becomes WP omega. It's an exercise of one line. Okay, so all these things are immediate consequences of what we said, so proof exercise. But the way the proof is in the notes, just I can't do everything. So a multiplication theorem in Morrey spaces, next section. A multiplication theorem. Problem, I give you two Morrey functions. Is it true that the product is Morrey? And we remember, so let me refresh our memory, let's say. So we remember that if you have P1, P2, which are numbers between 1 and plus infinity, it can be plus infinity also. And you know that 1 would be equal to 1 over P1, 1 over P2. The Hölder inequality implies that F comma G over P1 omega. The product of G is P. Okay, actually it's called the generalized Hölder inequality, okay? So we remember this fact and we are going to exploit it in one moment. We're going to exploit it to exploit. And also, you have also an estimate, right, to remember FG. We also have this, okay? To exploit it to prove the following. Let omega open. And then you take P1, P2 exactly as above. So you choose them so that you can use Hölder inequality, okay? And then you take two weights. Which can take the 0 value, that's okay. Well, V1, V2, not, comma, trivial. So I do not want V1 to be identically equal to 0. I do not want V2 to be identically equal to 0. Because in that case, there's nothing interesting going on in any case. And so the statement says that if you take F, which is in Morrey with the weight V1, sorry, number P1 omega, in G, it is the Morrey with the second weight, with the second P, omega. Then the product Fg belongs to the Morrey space with the products V1, V2. With the weight is the product of the weights. And here you put the P. So the very same that you need with the Hölder inequality for the product, as you expect, by the way. And not only we have some inequality, interesting inequality, that the Morrey modulus G rho with the weight products of the weights P omega can be estimated in terms of product of F rho V1 P omega G rho V2 omega. And this is going to be true for all possible rho's between 0 and even plus infinity. In particular, if you take the plus infinity, you have the inequality for the Morrey norms. It's going to be exactly equal to the norm. Okay, so now I want to prove this inequality. So, of course, the second inequality is an immediate consequence of the first inequality for rho equal to plus infinity. So it's enough that I prove the first inequality, which is easy to prove anyway. So what do we have always to do? We estimate the weight. What is the weight here? The weight in question is, sorry that something came up with V1, sorry. Product of the weights times what? The product Fg in the space LP bxr. We want to estimate it with the corresponding products, right? So this what equal then. Okay, now you remember Hölder. You write V1R, then I write the F LP1. This is Hölder inequality, right? Or beside, of course, that I switch the order of the factors V1 and V2. That's not important. But then you take the supremum on the right-hand side on all points x of omega in all positive r's between 0 and rho. This is less or equal than f rho v1 p omega g rho v2 sorry omega. This was v1. And the right-hand side. But now you look at the green only. Next, take the sup in XR in the green inequality. Which is what I just wrote now and obtain. Fg no, I'm sorry, I forgot the we were putting the row first. and then the corresponding P is a P, right? And that's it, end of the proof. So it was very, very easy proof, right? Just from the Lanza inequality, nothing else. And maybe we want to specialize this result here. This is a corollary that you could prove independently of this theorem. But anyway, it's a multiplication theorem, which is going to be useful for us if you want to work on Morrey spaces. And so let's say that this, let P, using usual N. Now you don't take P1 and P2, you take only P. And you also can be infinity, of course. And W is going to be a weight, a non-trivial weight between 0 plus infinity. Non-trivial. I don't want to take care of the zero case. And so the statement is, if Fg belongs to the Morrey times L infinity, so then product Fg is in the Morrey. So you can also say that MW is an L infinity module. So when you multiply an element to the Morrey times an essentially bounded function, you get a function in the Morrey. And as I said, we could prove this directly, but just you can also do it as an exercise by using the previous proposition so that we remember it. That's it. And the Fg in rho W P omega is less or equal than the F rho W P omega times the G in L infinity. And this is for all rho's, including, by the way, plus infinity. So in particular, for the case plus infinity, this becomes exactly Fg Morrey W P omega less or equal than F Morrey W P omega times G L infinity omega, right? Now you look at this inequality and you consider the case in which rho is not plus infinity, but just a positive number. If you know that F is vanishing Morrey, it means that the modulus here of F I'm underlying now is goes to 0 as rho tends to 0, and of course then as a consequence also left hand side goes to 0. Thus, in particular, if F is in the vanishing Morrey, then EFG is in the vanishing Morrey. And it's an immediate consequence of the inequality, because if the right hand side goes to 0, then tends to 0, then also the left hand side tends to 0. Okay, so and now we can deduce some consequences for our preferred weights by applying the above theorem, multiplication theorem, that's right. To our preferred weights. Remember which are our preferred weights. The W lambda rho, sorry, the R to the minus lambda, and the W lambda. We obtain the following, which is really an exercise at this point. So if you want corollary. And now you take always omega in a n, p1, p2, in 1 plus infinity. And not only p1, p2, but also p. And 1 will be. And then you take a lambda, lambda 1 and lambda 2. And you set lambda equal to the sum. Then let's write the statement, statement I if you want. If fg are in Morrey, by the way, rho here positive. G are in Morrey r to the minus lambda 1 rho p1 omega times, sorry, Morrey r to the second weight implies the product. Morrey, according to the theorem, I have to write the product of the weights, but r to the minus lambda 1 times r to the minus lambda 2 makes what? R to the minus lambda 1 plus lambda 2. And this is lambda. Comma rho p omega. I wrote p exactly as in the theorem. Then I use the second weight, the r to the minus lambda. And here the other rho, yes. So Fg. These are the so-called homogeneous Morrey spaces. Implies the products by the theorem belongs to Morrey. I make the product of the two, so I have r to the minus lambda, as I said. Because r to the minus lambda 1 times r to the minus lambda 2 makes r to the minus lambda. Here I have a p omega. Then 3. You have g. You remember that when the weight was m lambda, we called the space m lambda 1 p omega times p1 m lambda 2 p2 omega implies fg lambda p omega. This corresponds to the weights w lambda 1, w lambda 2. Moreover, if one of the factors is in a vanishing Morrey, then if at least the product is in the vanishing Morrey. Okay. And then you can also write the corresponding consequence with the infinity, right? And then we have a corollary of the above corollary, or the above corollary. Remember, the above corollary said that if you have a Morrey function, you multiply it by L infinity function, you get a Morrey function. And if the function in the Morrey is in the vanishing, then the product times an infinity function is in the vanishing. Remember. So the corollary is that Fg belongs to m r to the minus lambda 1. Oh, we use lambda only. We use lambda. Okay, so lambda p omega times n infinity implies that fg is Morrey. Here is rho. And fg was in Morrey R. This is the homogeneous version, so omega times n infinity omega. Fg belongs to mr to the minus lambda omega. And these are our preferred examples. So and Fg in the m lambda p omega times n infinity omega times Fg is the same. Over if F is also in the vanishing Morrey, so is Fg. Proof. Well, proof of this, it suffices to take, well, you just applied the previous one. So by the way, here, did I say a word of proof here? Oh yeah, I did not, but this is exercise. And you take V1 equal to W, and you take V2 equal to 1. Okay, you do this a 2 lines exercise, which is also written in the notes, by the way. Next, we turn to the problem of the embedding. So we did multiplication, now completeness, multiplication, embedding theorem. For Morrey spaces. Okay, so we are interested into the question. V1, let's say. Okay, this is what we are interested in. So we will have to estimate. In terms of I'm sorry, B2 here. Because you want this embedded into this, right? To unsolve V1. This is the job that we have to do later. And to estimate this one, in terms of this one, we use Helder. So we can estimate. In terms of LF, LP, XR, which is certainly of finite value volume, right? If, you remember, if P is greater or equal than Q. So in what I will have to say in a few minutes, I will take P greater or equal than Q for this reason. And I will also make another comment that at the end of the game, I will have to estimate V2 here times something in terms of V1, times maybe R or something. But unfortunately, to, let's say, state the condition to have this control, I must not forget that the V1 and V2 can vanish. In particular, also V1 can vanish. So I will have to be a little bit technically careful about it, okay? So you will not be surprised if I write what I'm going to write now. So, theorem. So omega, again, subset of Rn open, no condition on volume, nothing. P comma Q and 1 plus infinity, and I take P greater or equal than Q. And I already explained to you why we will need P greater or equal than Q. And then V1, V2, that V1, V2 weights, and they can vanish, but not identically, otherwise it doesn't make any sense to do all this business. V1, V2, non-trivial. And now I introduce this set, which may look awkward to you, but I will explain to you. I introduce the set I, P, Q, or O. And is the set of constants, positive constants, such that the inequality, following inequality is true. V2 R n over Q. That's equal than the constant V1 R n over P. For all R's between 0 and rho. Now I will explain one moment before I proceed. Then I write iota or PQO as the infimum of I PQO. Going to be for all positive rows, but also plus infinity if you wish. Now, you may wonder why I wrote this. You see, there is a need to estimate V2 R n over Q in terms of V1 R n over P times a constant. And you say, why didn't you just make a condition of the type that V2 R n over Q divided by R1 V1 Rn over P is bounded, okay? By a constant C, if you wish, but bounded, without, introducing all these nonsense. Answer, because I cannot divide by V1, because V1 may be 0 here and there. So I cannot do it. I have to resort to this long notation here, which may bother somebody. Okay. So let me say now the theorem, because not so far we have only said, put down some notation. So if rho is between 0 and plus infinity, and the set I PQ rho is not empty. Why do I need this? Because I need that exists at least one constant for which this inequality here is true. So I say this by saying that this set is not empty. So I have at least a constant at my disposal to estimate V2 times this in terms of V1 times this. Now you still ask me why that this and this. It will be clear in a few moments, okay? Then you can estimate the modulus of F, rho, with the weight V2 corresponding to the Q omega. In terms of this constant that we will have to compute later. Omega n, you remember omega n. Omega n is the volume of the unit ball in Rn, right? 1 over Q minus 1 over P. Since Q is less than P, 1 over Q is greater than 1 over P, and this exponent here is certainly positive. Iota PQ rho F rho V1 P omega. By the way, here they are common features. And this is true for all F's which are in Morley V1 P omega. Okay. In particular, if you assume that the IPQ of plus infinity is not empty, which means this assumption when rho is plus infinity, then you have this inequality when rho is plus infinity. But this means, remember that when rho is plus infinity, the modulus here on the left and on the right becomes really the Morrey norm. So you have that F M V2Q omega is estimated in terms of a constant, which is omega. And I don't care in this case, but in any case, I write it iota PQ plus infinity F M V1 P1 P omega, I'm sorry. P omega. And this means that M V1 P omega is continuously embedded into M V2 Q omega. And M V1 comma 0 omega is continuously embedded in M V2 Q omega with a 0 here. Why? Because if there are this modulus on the right hand side, F rho V2 P omega goes to 0, then also the one on the left hand side goes to 0. But if we further assume that I by itself tends to 0, 0 tends to 0, if we further assume that the limit F rho tends to 0 of iota PQ rho equal to 0, then not only you have that the little more, the vanishing Morrey is contained in a corresponding vanishing Morrey, but if you take the whole Morrey here, this is going to be contained in vanishing Morrey. Oh, why? Because if this factor here goes to 0, this remains finite, and then left hand side we're going to go to 0, so rather easy. Proof, let's prove the inequality now. I still have 5 minutes, I should be able to make it. So you want to control the norm, actually, or generally, you want to control the modulus corresponding to the weight V2 Q omega in terms of the corresponding one with V1 and P, right? So let's write it. This is Q. And now the first step, we are going to use Herder. This is the measure, the Lebesgue measure. Right? This is just the Herder inequality. Applied to the product F times 1. So sorry. Sorry that I have to generate the pages. And next step, let's write what the volume is. This volume here is. Remember that this volume here is going to be omega n times R to the n, right? Okay, so this is actually less or equal than. So the volume of the ball intersection, so this is less or equal to. So because this is the volume of the ball to this power, right? But here I have the ball intersection omega. So I cannot write equal. Get something bigger. Now we use our constant C, okay? Since exists C greater than 0 such that you can estimate, do you remember, 2 R n over Q in terms of V1 R to the n over P. And with a constant C. Let's visit again the I to deduce it. The set I was really the set of constants such that V2 R n over Q can be estimated into C times V1 R n over P. So you understand well why that set. And here I realize that I have V2. Maybe I use a different color. Here I have V2. Sorry, maybe let me write it better because okay. Times R n over Q. And yeah, use back now. And look at the green part only. Right? Because of this one, times omega n. And I am left with what? I am left with R to the n, R to the minus n over P, right? And then this cancels out. Now I take the soup on the left and right hand side. I take in the soup. And I obtain what? The soup in the left hand side was really F rho V2Q omega less or equal than constant C times N 1 over Q minus 1 over P times F L, I'm sorry, rho V1 P omega. And next, I take the infimum on all possible C's. Take C in I in 0 and obtain that F rho V2 Q omega iota PQ rho omega n 1 over Q minus 1 over P F rho V1 P omega. And my time is over, but we proved already this statement here, this inequality here, which immediately
Хорошо, все, я разговариваю.
Inequality here, and these inclusions. So next lecture will be tomorrow, if I remember right.
Yes.
Yes, it's
tomorrow.
right.
Tomorrow, okay?
Tomorrow, yes, tomorrow at 4 p.m.
Okay, so and we will start
And-
again from this result and make some applications and then speak about modification, okay?
Okay, just in case I may not be available tomorrow, I will try, but I'm not sure.
No problem.
So I would like to express my very deep gratitude to Professor Massimo Lanza de Cristoforis for these nice lectures. But still, I will try to connect myself tomorrow also. But just in case, thank you very much.
Thank you very much for listening to me, and see you tomorrow then. Okay.
See you tomorrow. Thank you. Bye.
Bye. Bye. Bye. Bye. Bye. Bye.